Okay, so the next thing we want to do now is to look at our spectrum image dataset and visualize it. And we have a number of tools to do this, which we'll look at now. And this brings us on to the first task in the analysis lab, to open and explore an EELS spectrum image using the slice tool. So we already have our spectrum image example, but if you don't have it open, you can open up the dataset, which is in sample SI, STEM EELS SI, EELS spectrum image high loss. And that will then open up the same dataset as we have open currently. The first tool we're going to look at is the slice tool. So if you look on the left-hand pane where we have the image status palette and the display control palette that we've looked at before, you will see an additional palette is opened because we have a spectrum image frontmost, and that is the slice palette. And the slice palette has two handles. The top handle allows us to control and vary what energy loss plane we're looking at in our three-dimensional dataset. And as you can see, when I move it, the displayed information in our raster image display changes. So if you like, when we have a three-dimensional dataset that we're trying to visualize in a two-dimensional raster display, we can only look at a particular integration range in energy at any one time. And this allows us to vary that integration range and simply move it up and down in energy loss. And what's quite interesting as we move that slider up and down, as we go over various energies or energy losses, we can see certain phases become brighter and then become darker as we go up and down in energy loss. The second handle controls the width of the integration range of this energy loss plane. And so if we set it to its lowest value, and we can see the value of it here, it's currently at its lowest value of width 1 eV, and the reason it's 1 eV is because the spectrum image was acquired with the EELS spectrometer set up to have 1 eV per channel dispersion, hence that's the minimum. With just 1 eV integration window, we can see that the data is very noisy when we go up and down in energy loss. Hence, if we increase the width of this window, I'm going to increase it to about 60 eV. When we then go up in energy loss, because we're now integrating over a 60 eV energy window to get our energy loss image, we can see that it's not as noisy as before. So that's one tool that we have to visualize our data set. So this gives us a way, if you like, of seeing the spatial information and how the spatial information changes as a function of energy loss. However, it doesn't tell us an awful lot about the spectral data itself, which then brings us on to the second tool, which is by far a much more useful tool for exploring the data set, and that is the spectrum picker tool. And the second and final task in this lesson is to use the spectrum picker tool. So we're now going to do the task, open and explore an EELS spectrum image using the picker tool. So we have our spectrum image open already that we're going to explore, and I'm going to create a spectrum picker on this spectrum image. So to do that, I put my cursor over the spectrum image raster display, I right click, and we can see in the floaty that opens up here that there is a tool there which is called Spectrum Image Picker. If I click on that, what you'll see is my cursor is now changed to an icon of a spectrum, and if I click on my spectrum image, what we'll essentially do now is pluck out the spectrum which is contained at this point. Now there are a couple of things to note here. The first thing to note is that this spectrum which has been plucked out is very noisy. We can see it's quite hard to make out any features. There's a core loss edge here at approximately 550 eV loss, but it's got an awful lot of noise in it. Another thing to notice now is that it's quite easy to see the energy loss range of the spectrum. It is going from approximately 300 eV all the way up to about 2400 eV loss. So it's a very large energy loss range contained in a single spectrum. And we can also see that within that spectrum there's a very large decrease in the intensity as we get to the higher losses. One thing to keep in mind, of course, is that this is a STEM spectrum image. The way it's been acquired is rastering a probe across our sample and acquiring an EELS spectrum at each point. And that is what we're seeing here, just one of those spectra that was acquired, the one that was acquired at this point. Now we can move our picker tool by left-click dragging, and we can see how the spectra change from pixel to pixel. And within this phase, that spectrum doesn't seem to change much, but as we enter an adjacent phase, we'll see that the spectral details change quite abruptly. And that's because we've gone from a region of one composition to a region of a different composition. Now this spectrum is very noisy, and the reason it's very noisy is it's just a single spectrum which was acquired at 2 milliseconds. And so even though there's some spectral information in there, it's been acquired very quickly, and so there's not that much intensity. To improve the quality of the spectrum that we're looking at, what we can do is grab on the handles of the picker tool and drag, and we'll open up that ROI, and our spectrum now looks much better, and that's because it's now summing all the spectra which are within this ROI rectangle. Now when you create an ROI on an image, the control palette down here tells you information about that particular region of interest. Now, these are currently in calibrated units. If I were to go to the image status palette and disable the calibration, we can go down to the control palette and we can see that the ROI that I've created is of width 11 pixels by height 11 pixels. We're now summing 121 spectra within this summed spectrum. Some other things that we can do to aid visualization of our spectrum is that this splitter handle, we can move that across, and what we can see now is that whereas we thought we just had one edge before that we could see, now that we've integrated over many spectra, it's now apparent that there is a second edge in the spectrum at a much higher energy loss. So we have one edge here, which is at about 530 EV loss. Most likely is the oxygen K edge. And as we go up to the higher energy, at about 1840 EV loss, we can see another kind of sharp edge, which is most likely the silicon K edge. We'll learn later in the week how we can identify those edges. And accordingly, if we move the picker tool, we'll see that there are different shaped edges at different energies at different points in our spectrum image. One other thing that can be useful when looking at a spectrum over a very large energy loss range is to use the log scale. And if I enable the log scale via the display control palette, the log scaling makes this a very convenient way to see the various edges in the spectra as I move the picker tool around the spectrum image, even though the spectra might be varying quite significantly in intensity. Now, one thing that is interesting to note is, as mentioned, this is a spectrum which has been integrated over this full region here within the ROI. If I were to now close it back down to look at a single spectrum, you can see how noisy the spectrum is now. That silicon K edge that we were looking at 1840 EV is barely discernible. And I want to show you a second and perhaps more convenient way that we can create that picker tool. So I'm just going to close this spectrum, and you'll notice that when I close the spectrum, the picker tool disappears. Instead of using the right-click floaty to create my picker tool. There is a keyboard shortcut to do this. You can simply hold down Control, left click and drag on the spectrum image. And that will straight away create my picker tool. Create a picker tool. If I repeat, it'll create a second picker tool, and you can have as many picker tools as you like on a spectrum image. If I close a spectrum, then the associated picker tool that was with it also disappears. Alternatively, if I were to delete the ROI, the spectrum that is associated with that picker ROI doesn't close, but it's now separated from the spectrum image. And so that can be very useful if you wanted to pluck out a spectrum from your spectrum image, but then not have it updating when any ROIs are moved. You can just remove the ROI. One final thing I want to show you is how we can link together the information that we see in the slice palette with the spectral information that we see with the picker tool. So in order to do this, I'm going to create another picker spectrum. I'm going to make sure that the picker spectrum is frontmost, and then if I go over to the slice palette, there's a checkbox here which says show range. So I check on that. And when I check on that, you can see now that there is a slice ROI which is created. And this slice ROI is at the energy loss and set to the energy loss width corresponding to these two handles in the slice palette. And these two things are linked dynamically. So if I move the slice handle, you can see now that my slice ROI moves up and down. I can also change the width and also interact directly with this ROI, and the handles change appropriately. What we're seeing is this ROI that I am moving, the integral of the spectrum within that ROI for every spectrum in the spectrum image is giving rise to the contrast that's shown in this raster display. And this can be super useful. It allows us to look at the contrast mechanism within this energy loss image and how it relates to the core loss edges or the spectral features that give rise to it. So I'll show you an example. If I were to move this slice tool up and down, we'll see that that phase on the right hand side is dark at this region and then becomes bright here. So as the window, the integration window, goes from about 900 EV loss to about 1000 EV loss, there's a big jump in the intensity in this region here. So if I put my picker tool in this region, we can straight away see why. The reason is that before this edge, which is shown at about 930 EV loss, it's dark, and after the edge, it's bright. And that's because everywhere in this spectrum image which contains the element corresponding to this edge becomes brighter once we move our window on top of that edge, because it gets that extra edge's intensity. And this is rather important. This gives us an insight into how we can calculate elemental maps later in the week. It also gives us insight into the kind of contrast mechanism that you'll see when you're doing, for example, FTEM imaging or FTEM 3 window maps. Before the edge, it's not so bright, and then after the edge, it becomes bright. And then if you do appropriate processing, you can pluck out that core loss intensity and have something which we would call an elemental map. And that concludes this introduction to STEM spectrum images. Thank you.